Black holes are the most extreme objects in the universe, shattering everything we know about physics and going beyond. From infinitesimally small centers and fatal radiation, to light warping and galaxy destruction, nothing about black holes can be understood with logic and common sense. So let's explore the mind-numbingly complex science surrounding the objects that shatter space-time itself. Happy birthday, black holes in a nutshell. A black hole is a region of space-time where gravity becomes so strong that not even light can escape it. Essentially, a black hole is an object whose escape velocity, the minimum speed required to escape an object's gravitational influence, is greater than the speed of light. Since nothing can travel faster than the speed of light, nothing can escape a black hole. But how do you create a black hole? Einstein's theory of general relativity taught us that what we experience as the gravitational force is actually the bending of space-time itself by matter and energy. We have gone into more of this in our Answer to Literally Everything special video of 2023. In a nutshell, if you compress enough matter or energy into a small enough volume, the fabric of space-time is warped so much that it collapses into a point of infinite density. The minimum radius a certain mass can be compressed to until it collapses into a black hole is called the Schwarzschild radius, which is equal to 2gm over c squared, where g is the gravitational constant and c is the speed of light. In principle, all objects can be turned into black holes if they are squeezed past their Schwarzschild radii. For the Earth to become a black hole, it would need to be compressed into a sphere smaller than a dollar coin. Since it takes so much energy to compress an object to its Schwarzschild radius, everyday objects won't just randomly collapse into black holes. However, in some extreme circumstances, the conditions are just right for a black hole to form. Most black holes form when massive stars die in a supernova explosion. We've explained more of this process in our Stars series. In summary, during the final moments of the most massive stars, the extreme mass of the star's outer layers causes the core to collapse, detonating the outer layers into a cataclysmic explosion that outshines entire galaxies. If the mass of the stellar core is greater than 2.2 to 2.9 solar masses, called the Tolman-Oppenheimer-Volkoff limit, the core will collapse into a black hole. The anatomy of black holes. Black holes come in a range of different sizes, from hypothetical miniature objects smaller than protons to the largest single bodies in the universe. However, all black holes can be fundamentally described by their mass, spin, and electric charge, a bit like elementary particles. What's more, all black holes have similar physical features. The edge of a black hole is its event horizon, the point of no return. Once anything crosses the event horizon, it can't escape. The radius of the event horizon is the Schwarzschild radius. At the center of the black hole is the singularity, a point of zero size and infinite density where all the mass of the black hole is concentrated at. The curvature of space-time at the singularity becomes infinite, which is why all our laws of physics are unable to describe it. Things can orbit black holes, just like planets can orbit stars. If enough matter is drawn around the black hole, collisions between the orbiting objects force it into a flat, ring-like structure called an accretion disk. Around 5 to 10% of all black holes have accretion disks, and because of the insane gravity around black holes, matter can be accelerated to significant fractions of the speed of light. The innermost stable circular orbit, or ISCO, of an object around a black hole is the minimum distance from the black hole in which objects can maintain a stable orbit around it. The radius of ISCO is 3 Schwarzschild radii, or 3 times larger than the event horizon. This also means that the inner edge of the accretion disk is ISCO. Although ISCO is the minimum distance matter can stably orbit around black holes, light can orbit even closer. At 1.5 Schwarzschild radii is the photon sphere, a region where the black hole's extreme gravity allows light to orbit around it. These orbits at the photon sphere are not stable though. After a while, the photons either fall into the black hole or are shot off to infinity. Because of the severe gravity around the black hole, up to a certain distance, all paths that light can travel through end up falling into the singularity. At 2.6 Schwarzschild radii, the light ray barely grazes the photon sphere and can shoot off elsewhere. This creates a dark region 2.6 Schwarzschild radii wide that is called the black hole shadow, and this shadow is what the dark spots in the black hole images are. What would happen if you fell into a black hole? Try not to die. Falling into a black hole. As you approach a black hole, the first thing you would notice is the extreme brightness. Collisions between particles in the accretion disk heat matter up to millions of degrees, creating brilliant light shows across all parts of the electromagnetic spectrum. What's more, because the matter in the accretion disk is traveling close to the speed of light, objects orbiting towards you appear much brighter than objects moving away from you. You won't be able to enjoy it for long though. Exposure to extreme radiation, particularly X-rays and gamma rays, can cause radiation sickness or even death. After you cross the ISCO of this black hole, your orbit will begin to decay towards the event horizon. Any signals you send out to external observers will be stretched to longer and longer wavelengths, a process called redshift. To outside observers, you will appear redder and redder. After falling for a bit longer, you reach the photon sphere. Because of the orbits of the photons around black holes, you can actually see the back of your own head. Hold on, something strange is happening. The universe around you seems to be speeding up. The closer you are to the black hole, the faster time seems to be passing for the rest of the universe. What is happening? General relativity taught us that time flows slower for people in gravitational fields, something we call time dilation. This is also true on Earth. Time passes fractions of milliseconds slower for people living at lower altitudes than people living at higher altitudes. In fact, satellites have to be adjusted to account for time dilation. Black holes possess the strongest gravitational fields in the universe, and as a result, you would experience extreme time dilation. A few minutes passing by for you means that eons have passed for the rest of the universe. To outside observers, you would seem to move slower and slower, redder and redder, and fainter, eventually appearing as if you froze in place. Sadly, that would be the least of your problems. After you cross the event horizon, a painful death by spaghettification would gleefully await you. Because of the extreme gravity and density of black holes, tidal forces would rip your body apart. If you fall in feet first, your feet would experience a much stronger gravitational pull than your head, brutally stretching your body into a long, thin, spaghetti-like strand, ending your journey. Spaghettification is only a risk with smaller black holes though. For the sake of science, let's assume that you picked a supermassive black hole where spaghettification isn't a problem until well after you cross the event horizon. So what would happen once you crossed its event horizon? Inside the black hole, space-time is so horribly broken that time travel is possible, on what physicists call closed timeline curves. Not only that, space and time seem to reverse their roles inside of black holes. Nothing can escape a black hole because all paths end up in the singularity. But this is because the singularity lies in the future of all objects, and the event horizon in the past. Whatever you do, you will continue falling towards the singularity until you eventually become spaghettified. The information paradox. Black holes are the source of a 50-year-old paradox that risks shattering all of physics. Information is a property of particles that relates to disorder, encryption and decryption, and the evolution of quantum systems. Information cannot be destroyed, according to quantum mechanics. Yet black holes do just that. All information about objects that fall into a black hole is seemingly destroyed, as the rest of the universe can no longer access it. To complicate things even more, Stephen Hawking discovered that black holes have a temperature. Empty space is not actually empty, but boiling with quantum fluctuations on quantum fields that constantly produce particle-antiparticle pairs that exist for a split second before annihilating. These virtual particles actually serve an important role in understanding three of the fundamental forces. When virtual particles are created at the event horizon, one particle will fall into the black hole while the other escapes, stopping the annihilation. This surviving particle steals a tiny bit of mass from the black hole and is called Hawking radiation. These virtual particles are being produced relentlessly around black holes, which slowly eats the black hole up. After an obscenely long time, this Hawking radiation will inevitably make the black hole evaporate in a spectacular explosion. This is precisely what stresses physicists. Hawking radiation will eventually cause the black hole to disappear without a trace, which means that all the information stored inside of the black hole will be destroyed. This is the information paradox, and it risks undoing physics in countless fields. So what are some solutions to the information paradox? Well, there are many proposed ideas. For a long time, black holes were thought to be bald. The no-hair theorem proposed that black holes could be fully described by the three characteristics we listed before: mass, spin, and electric charge, and nothing else. This is precisely the cause of the information paradox. However, some scientists suggested that black holes could be hairy. In what is called the yes-hair theorem put forward recently, some scientists suggested that information about what fell in could be stored as quantum hair, an imprint of the object on the gravitational field of the black hole. Escaping Hawking radiation could tell us about this quantum hair, and as a result, information would not be lost. Others have proposed that, because of the quantum nature of virtual particles, Hawking radiation could be entangled with information inside of the black hole, which could mean that all information stored inside of the black hole could eventually come out again. Physicist Don Page devised the Page curve as a model to describe this. Variants of this theory give rise to a firewall inside of the black hole. Rather than there being empty space-time inside of the black hole, this theory suggests that as soon as something crosses the event horizon, they are swiftly incinerated by a wall of high-energy radiation. The information about the object is said to be stored in the firewall. Some scientists believe in the fuzzball theory. Rather than viewing black holes as infinitely dense singularities surrounded by inescapable event horizons, the fuzzball theory hypothesizes that black holes are balls of strings. In a sense, while white dwarfs and neutron stars are made of electron and neutron degenerate matter respectively, fuzzballs are made from degenerate matter composed of strings. Interestingly, fuzzballs don't need event horizons and singularities. The fuzzball resembles a planet or a star. In addition, the fuzzball seems to be able to store information in the form of these fuzzy strings. Yet other theories call for wormholes. Connections between the interior of black holes could give rise to conservation of information and create a region inside of the black hole known as an island. Even though everything on this island is also inside of the black hole, it is technically not a part of the black hole, leaking information elsewhere. Finally, black holes may be holograms. Astronomers know that the surface area of a black hole is more important than its volume, leading some to speculate that information could be stored on the two-dimensional surface area of the event horizon. Consequently, black holes can be understood as holograms. Sadly, while these ideas are fun to play with, as of the production of this video, all of these theories either lack observational proof or are inconsistent with our current laws of physics, meaning that the information paradox is still unresolved. Throw away your sanity. Spinning black holes. We need to come clean. We've been grossly glossing over things. Up until now, we've been describing non-rotating black holes, sometimes called Schwarzschild black holes, because they are so simple. In reality though, all black holes are spinning, as their parent stars were spinning as well. And black holes are some of the fastest spinning objects, spinning at nearly the speed of light. This extreme rotation causes some interesting changes to the black hole. A Kerr black hole, or a chargeless spinning black hole, has two event horizons, the inner and outer horizons. While the outer horizon is like the normal event horizon of a non-spinning black hole, the inner horizon, sometimes called the Cauchy horizon, is the boundary where predictability breaks down. What's more, because points can't rotate, the singularities of Kerr black holes are not zero-dimensional points but one-dimensional rings that have zero thickness and a finite radius. This ringularity is where all the matter in the black hole is stored. The photon sphere is just as wild. In Schwarzschild black holes, there is one photon sphere. In Kerr black holes, there are two photon spheres, the co-rotating and counter-rotating photon spheres. Photons that orbit in the same direction as the rotation of the black hole, called prograde motion, are stable, while photons that orbit in the opposite direction, called retrograde motion, are more unstable. In general, the co-rotating photon sphere is further from the event horizon than the counter-rotating photon sphere. The extreme rotation, combined with the black hole's strong gravitational field, twists and drags space-time itself in a process called frame dragging. This frame dragging creates a region called the ergosphere outside of the outer horizon, where space-time itself swirls like a whirlpool faster than the speed of light. The outer boundary of the ergosphere is called the static limit, which barely grazes the event horizon at the poles but bulges outwards near the equator. This means that anything inside of the ergosphere is forced to rotate around, which can be used to extract energy from the black hole. Things can enter and leave the ergosphere if they're traveling fast enough. In some cases, the rotation of the black hole interacts with its magnetic field. The field then draws some of the matter in the accretion disk and funnels it into narrow jets at the poles that can extend for hundreds of thousands of light years, accelerating matter to more than 99.99% of the speed of light. Scientists think that these relativistic jets are the source of cosmic rays, high-energy particles that hit us from space. 10% of all black holes have relativistic jets, the largest, brightest, and scariest objects in the universe. Black holes that are hundreds of thousands, millions, or even billions of times as massive as the Sun are called supermassive black holes. Almost all galaxies have a supermassive black hole in their centers. We actually have photos of two supermassive black holes, as of the production of this video, Messier 87 star from the galaxy Messier 87, and Sagittarius A star from our very own Milky Way. Sometimes exceptionally powerful supermassive black holes radiate extreme energy, create powerful galactic hurricanes, and eject billions of tons of matter with humongous relativistic jets. These are called active galactic nuclei, and the light they emit alone can outshine its entire galaxy. AGNs are powered by their luminous accretion disks. As matter in the accretion disk spirals into the black hole, it is heated up to exceptional temperatures, allowing it to radiate across the electromagnetic spectrum. Even among AGNs, there are some extraordinary black holes. Quasars are a type of AGN that are especially bright, consuming galaxies worth of matter. The hottest known quasar is over 10 trillion Kelvin, which is comparable to the universe right after the Big Bang. Quasars are so powerful that they are thought to be able to destroy galaxies and reshape the structure of the observable universe. Some quasars have powerful relativistic jets that are pointed nearly directly at us. We call those blazars. This means that all blazars are quasars, but only some quasars are blazars. So how do these behemoths form? Supermassive black holes are at the center of another mystery in astronomy. They shouldn't exist, but they do. Black holes that form from supernovae are not massive enough, and the way black holes grow, consumption of matter and black hole mergers, are too slow to account for how early supermassive black holes existed in the universe. One idea is the quasi-star. Quasi-stars are hypothetical objects that could have formed in the baby universe, where extremely massive gas clouds could have ignited into unimaginably large stars, many times larger than the largest stars we know today. This extreme mass would have been highly unstable, pressuring the core until it collapsed into a black hole. Unlike modern-day stars, because of its sheer mass, the quasi-star is not blown away by the collapse of the core. The black hole at the heart of the quasi-star begins gorging on the great mass around it, which makes it grow in size and radiate energy. This radiation is so powerful that it can push back against the weight of septillions of tons of hot plasma and stabilize the star. After millions of years, the black hole will cause the quasi-star to cataclysmically explode, releasing it to allow it to continue growing into supermassive black holes. Conclusion. Ultimately, black holes are the most powerful, most massive, most mysterious, and most dangerous objects in the universe, influencing galaxies and toying with space-time itself. Countless paradoxes surround them, which is a wake-up call to remind us of how there is still work to be done in physics. There are several things to keep in mind after watching this video. Black holes are at the center of unknown physics, where general relativity meets quantum mechanics. In fact, black holes are one of the reasons why a theory of everything in physics is needed. As a result, new research is constantly being made in the field that rewrites past theories. Most theories, particularly the solutions to the information paradox that we talked about in this video, should be treated with a grain of salt. Oversimplification of such a complex topic doesn't quite do black holes justice. To learn more about them yourselves, take a look at our bibliography linked in the video description below. Photos of the two black hole images are also linked in the video description. To understand the life cycle of stars, quantum fields, general relativity, degenerate matter, and the theory of everything, take a look at our past videos around that topic, listed in the video description. This was our second special video and last video of 2023, marking the end of another era of the Information Institute. 2023 revolutionized our channel in many ways. We've produced nearly 3 times as many videos as last year, and each video's audio, camera, and editing quality were significantly improved from last year's. We also launched our first podcast, Lively Live Life, uploading its 15 episodes once every 2 weeks from late May to early December. All episodes are now streaming on YouTube, Spotify, Google Podcast, Apple Podcasts, Podbean, and Amazon Music. After working overtime, we also released 2 special videos, detailed documentaries. The first 3 videos we have produced have also been improved and re-uploaded as 3 remixes. The Worst Crime in Human History, What Makes You You, and You're Made From This are some of our essentials from this year. The Information Institute plans to change course next year. To save time for a busy schedule, we will be releasing a few long special videos that will give an immersive tour of a particular field of science. More details are to come sometime next year. Thank you for sticking with us for the past 2 years. See you in 2024.